Okay, let's unpack this. Imagine a world where artificial intelligence doesn't just, spit out code, but actually understands it, thinking through complex problems with a kind of internal logic. Maybe even having its own aha moments, correcting itself.
Yeah, it sounds like sci-fi, doesn't it? But it's really not that far off anymore.
Exactly. That's the incredible frontier we're diving into today. The pace of AI innovation, especially in specific areas like, well, advanced coding and mathematical reasoning, it's just staggering. We're
Right.
talking about models that are moving beyond just mimicking stuff to showing, well, genuine understanding, real problem solving, and some pretty sophisticated generation.
And what's really fascinating here, I think, is how these models aren't just inching forward on performance benchmarks. They're fundamentally changing how we even think about training AI and how they demonstrate what you could genuinely call emergent intelligence. So our mission today, really, is to dig into the research behind these models,
Mm.
pull out the most important, maybe paradigm-shifting bits for you, give you a shortcut, basically, to understanding this rise of code and reasoning intelligence.
And where are we digging? What are the sources?
We've been deep diving into the foundational research papers from Deepseek AI. They detail their groundbreaking work on the Deepseek series of large language models, specifically Deepseek Coder, Deepseek Math, and the really interesting one, Deepseek R1.
Okay.
It's not just about what they can do, which is impressive enough, but how they got there, and maybe more importantly, what that means for you and the future of AI.
Absolutely. So let's kick off with Deepseek Coder. What was the big problem they were trying to solve there? Because it feels like the AI coding space was pretty crowded already.
Well, yes and no. For a long time, the really advanced stuff, especially for code development, was dominated by closed source LLMs.
Right, the big proprietary one.
Exactly. And think about it. If you're a researcher or a developer or maybe a startup trying to innovate, having these powerful tools locked away,
Yeah.
it's a massive bottleneck.
Yeah, it really limits what you can build, what you can study openly. It kind of caps innovation, doesn't it?
Totally. It's like being given this amazing high-performance engine, but you're forbidden from ever looking under the hood, let alone tinkering with it.
You can't build on it easily.
Precisely. That whole community-driven improvement just wasn't happening at the scale it could have.
Okay, so DeepSeek Coder was the answer to that.
It emerges as a direct and pretty ambitious response. It's
Yeah.
not just one model either. It's a whole range of open source code models.
Mhm.
They vary in size strategically from a pretty compact 1.3 billion parameters up to a hefty 33 billion.
So options for different needs, different hardware.
Right. And what's really remarkable and shows their commitment is that they train these completely from scratch.
Wow.
On this enormous data set, 2 trillion tokens of code and related text.
2 trillion. That's
Yeah.
astronomical.
It's massive. And that scale, that dedicated training, let them achieve state-of-the-art performance among the open source models on lots of benchmarks. But here's the kicker.
Go on.
They actually started surpassing some well-established closed-source models you might know,
Hmm.
like OpenAI's older Codex, and even GPT 3.5 in certain coding tasks.
Seriously. Outperforming GPT 3.5 for an open source model.
In specific code generation and understanding areas, yes. It wasn't just incremental. It felt like a real shift in capability becoming available to everyone.
That's huge. It means open source isn't just playing catch up anymore. It's actually leapfrogging in some cases.
Exactly.
And you mentioned it's not just performance, it's about access, right? Democratizing it.
Absolutely. And a crucial piece here, one that directly empowers you listening, whether you're a developer, researcher, entrepreneur, is the license. It's incredibly permissive.
Not just for academics.
No, not at all. You can freely use these models for academic research and for unrestricted commercial use. That's big.
That really opens things up.
It does. Imagine integrating these powerful coding tools directly into your workflow, your products, without the usual licensing headaches, the API costs, the vendor lock-in worries.
Yeah, it fosters a whole different kind of innovation, more community driven.
That's the idea.
Okay, now this is where it gets really interesting for me. How do you actually teach an AI to be an expert coder?
Yeah.
Going beyond just predicting the next line or completing a little snippet,
Right.
understanding a whole project with all its interconnected files. That seems like a massive jump. What was their secret sauce in the training?
It was definitely meticulous
Yeah.
and quite innovative. They started with what they called a high-quality project-level code corpus.
Mm.
So pre-training on this huge data set covering 87 programming languages.
87. Okay.
But the real game changer, what sets Deepseek Coder apart from a lot of older models, was the repository-level data
But
construction.
repository level, meaning,
Well, think about how models used to be trained often on isolated code files, right? Like each file was its own little island.
yeah, that doesn't sound like real world coding.
Not at all. Real code lives in projects. It has complex relationships between files. Import in Python using in C#, include C++, plus DO. These aren't just random lines. They define how everything connects.
So ignoring that context really limits how useful a model can be.
Hugely. It limits
Yeah.
its ability to grasp the bigger picture of a coding task.
So they somehow taught the model, the architecture, the interconnectedness. How did they manage that? That sounds incredibly complex from a data perspective.
It was a big undertaking. They didn't just feed it raw code. First, they parse all the dependencies between files within entire software repositories. Then, and this is key, they arrange these files in a specific topologically sorted order.
Topologically sorted, like independency graphs.
Exactly like that. It ensures that the context of file needs anything it imports or includes appears before that file in the training sequence.
Ah, so the model sees the dependencies before it sees the code using them.
Precisely. They used a topological sort algorithm to figure out this correct sequence for each project. And they even added comments with the file path at the start of each file to preserve that structural context within the training data itself.
That makes the training data much closer to how you actually encounter code in a real project.
Right, which makes the model way more practical for your complex multi-file coding tasks.
Okay, that covers understanding the structure. But what about teaching it to write code smarter, especially filling in missing parts, which you do all the time in an IDE?
That's where the fill-in-middle objective, or FEM, comes in. This was a core innovation.
FNM, fill in middle.
Okay. Traditional models mostly do next token prediction, predict the next word or piece of code. FMM is different. It trains the model to predict missing code segments based on both what comes before and what comes after the gap.
Ah, using both prefix and suffix context.
Exactly. Imagine you're writing a function, you know the start and the end, but need the middle bit. FIM trains the model to use all that surrounding context.
That sounds incredibly useful for code completion, refactoring.
Definitely. Or even generating whole blocks of code. And to handle real-world code complexity, they significantly increased the context length the model could handle, up to 16,000 tokens.
16,000. That's quite a window.
It lets the models tackle much larger, more intricate coding scenarios, keeping track of more of the code base at once.
Now, with this FIM objective, did they just crank it up to the max? Was it a case of more FIM is always better?
You'd think so, wouldn't you? But no, and this shows the nuance in training these things. They ran careful ablation studies, testing different rates of something called permuted segment masking, PSM, which is part of FUM.
And what do they find?
Something quite counterintuitive. A 100% AM rate gave the best results on FIM-specific tests, sure, but it actually resulted in the weakest overall code completion performance on general tasks.
Really? So optimizing purely for FEM hurt its general coding ability.
It seems so. There was a trade-off. They
Yeah.
found that a 50% PSM rate hit the sweet spot.
50%.
Yeah. It kept strong FAM capability. It's still great at filling in the middle. But it also preserved and even boosted its general code completion skills. It just shows how these training decisions are a balancing act. Too much of one thing can backfire.
And of course, the classic AI problem. Garbage in, garbage out. You mentioned this massive 2 trillion token data set. How did they make sure it wasn't just, well, a pile of junk code from the internet?
Excellent point. Their data curation was incredibly rigorous, multi-stage, started with crawling public repos like GitHub, naturally, but then layers of filtering.
Like what?
First, rule-based filtering. Things like excluding files with ridiculously long lines or too few letters, probably not real code. Filtering out XML, HTML, JSON, YAML to keep it focused on programming logic.
Okay, basic cleanup.
Then the dependency parsing we talked about, organizing by repository. Then crucial repository-level deduplication. You don't want the model just memorizing popular projects, and you definitely don't want test data leaking into the training set.
Right, that would invalidate the benchmarks.
Absolutely. Yeah. But then came the really sophisticated part, quality screening.
How do you screen for quality automatically? That sounds hard.
It is. They used a combination, a compiler to catch syntax errors, a specialized quality model to look for things like poor readability or bad structure, and heuristic rules.
So multiple checks.
Yeah, a multifaceted approach. The final data set, 798 gigs, 603 million files across those 87 languages, was huge, but also incredibly refined. And one more critical detail for you thinking about benchmark fairness: decontamination.
Decontamination.
They use stringent n-gram filtering, looking for specific sequences like 10 words or even 3 exact words in a row to ensure their training data didn't contain chunks from common test sets like human evil, MBPP, or math benchmarks like GSM-8K or math.
So no cheating, making sure the model is genuinely solving the problems, not just remembering the answers it saw during training.
Precisely. It's like ensuring a student hasn't seen the exam questions beforehand. It validates the results.
Okay, so all this work, the project level context, the FIMM, the intense data cleaning and decontamination, did it actually pay off? What did the benchmarks show?
Oh, absolutely. The
Yeah.
results were quite something, especially for open source. On standard code generation tests like Human Evil and MBPP, the Deepseek Coder-based 33B model was consistently top tier.
Even the smaller ones.
Get this, the 6.7 billion parameter model actually outperformed Codalama 33B, a model 5 times its size, on these tasks.
Wow.
And when they fine-tuned it with instructions, the Deepseek Coder Instruct 33B version, it even managed to outperform OpenAI's GPT 3.5 Turbo on Human Evil.
Outperforming 3.5 Turbo again? That's a recurring theme.
It significantly narrowed the gap to even more advanced models like GPT-4. A huge win for open source, showing top-tier code AI can be accessible.
Truly remarkable for open source. But okay, generating code snippets is one thing. What about more interactive conversational coding, like when you're talking back and forth with an AI assistant refining code?
Another area where the Instruct version really demonstrated its practical value. The research paper shows examples like building a snake game with pig game, or doing data analysis on a student database.
Uh-huh.
In these multi-turn chats, the 33B Instruct model didn't just give one-off answers. It provided complete, bug-free, well-explained solutions that evolved over several turns.
So it remembered the context, understood follow-up requests.
Exactly.
Ooh.
It's not just spitting code. It's engaging in a dialogue, refining, extending. Super useful if you're working on something complex and need that kind of collaborative partner.
And what about the really hard stuff, like competitive programming problems, the kind that stump even good human coders? Leet code style.
They tested it on a tough lead code contest benchmark. Crucially, this included out-of-domain problems it hadn't seen before, really testing generalization.
How'd it do?
Well, there's still a gap compared to the absolute top models like GPT-4 Turbo, naturally. But Deepseek Coder Instruct 33B was the only open-source model to actually beat GPT 3.5 Turbo on this benchmark.
The only one?
The only one, with a pass at one score of 27.8%. It shows it has robust problem-solving skills on genuinely complex, novel coding challenges, really pushing the open-source boundary.
So for you listening, if you're tackling complex coding problems, what's a practical tip from this research? How can you get the best out of these models?
Yeah, there's a really powerful, simple takeaway, and it involves chain of thought, or COT prompting.
Ah, CPT. Tell me more.
The researchers found that just adding a simple instruction like you need first to write a step-by-step outline and then write the code significantly boosted performance, especially on harder problems.
Just asking it to think step by step first.
Pretty much. It forces the model to break down the problem, plan the logic before generating code.
Mm.
This structured thinking often leads to much better, more coherent, less buggy results.
So don't just state the problem, ask for the plan first. That's a great tip for anyone using these models.
Definitely worth trying if you're hitting complex tasks.
And it wasn't just a coding specialist, right? You mentioned it also showed surprising skill in math. Program-based math reasoning. That sounds like a bridge to something deeper.
You're absolutely right. It wasn't just generating standard software code. Deepseek coders showed this impressive, maybe unexpected, ability to solve complex math problems by generating and executing code.
How does that work?
They use methods like PL, Program-Aided Language Models.
Mhm.
Basically, the LLM writes small executable code snippets, like Python scripts, to do calculations or logical checks. Then it interprets the code's output to guide its reasoning or get the final answer.
So it uses code as a calculation tool for math problems.
Exactly. They tested this on math benchmarks like GSM-8K, Grade School Math, and the much harder math dataset, competition-level math. The 33B model showed really remarkable potential here.
So it could be useful for scientific computing, data analysis, engineering.
Potentially, yes. It shows these models aren't just coding machines. They have deeper, more generalizable reasoning skills that go beyond just writing software.
Okay, let's unpack this next bit because it sounds, well, almost revolutionary. We usually think AI needs tons of human-labeled data to learn complex stuff, right? To learn how to reason.
That's the conditional wisdom, yeah. Supervised learning, fine-tuning.
But what if it could teach itself to reason from scratch? That sounds like the stuff of sci-fi, a real leap. Yet DeepSeek AI explored this with DeepSeek R10.
It is groundbreaking, and it really challenges that conventional approach. DeepSeek R10 was trained entirely using large-scale reinforcement learning RL, and crucially, without supervised fine-tuning first.
No initial examples of good reasoning.
None. It had to figure out complex reasoning strategies completely on its own, just through trial and error,
Yeah.
guided purely by rewards for getting the right answer.
How do they even make that feasible? RL can be computationally brutal.
They used an efficient RL algorithm they developed called GRPO Group Relative Policy Optimization.
GOPO. Okay.
What's clever about GRPO is it gets rid of the need for a big critic model, usually another huge AI that evaluates the main model's attempts and uses a ton of resources.
Right. The critic is often as big as the main model.
Exactly.
Yeah.
Instead, GRPO estimates a reward baseline just from the scores of a group of the model's own attempts in a batch. It's like learning by comparing your attempts against your peers in that batch, rather than needing a dedicated tutor for every single try.
So much more resource efficient.
Massively so.
Yeah.
It makes this kind of advanced RL much more scalable and accessible.
Okay, so it's learning through efficient trial and error. What did they actually see during this pure RL process? Did it genuinely learn to reason?
This is where it gets really mind-blowing, the aha moment.
The aha moment.
During training, an intermediate version of R10 spontaneously learned to rethink its approach.
Sure.
It started reevaluating its initial steps, backtracking if needed, spending more internal thinking time when it sensed difficulty.
It learned metacognition, thinking about its own thinking.
It really looks like it. The paper even quotes the model's internal dialogue showing self-correction. Stuff like, wait, that's an aha moment I can flag here. Let's reevaluate this step by step.
That wasn't programmed in, it just emerged.
Emerged autonomously from the RL process, just from the drive to get the right answers. It developed a strategy for how to think, not just what to think.
Wow. That's a profound aha moment for us listening, too. It shows AI developing sophisticated problem-solving, even self-correction, just from incentives, not explicit instructions. Autonomous learning in action.
Precisely. And the performance lift was incredible. On the AME 2024 math benchmark, its score on the first try jumped from about 15% to 71%.
71%.
Just from RL.
Just from RL. And with majority voting taking the most common answer from multiple tries, it hit nearly 87%. That's matching highly capable human-supervised models achieved purely through self-evolution.
Incredible. But were there downsides to this pure RL approach? Any rough edges?
Yes, despite the amazing reasoning power, R10 had practical issues. Its internal reasoning steps, while effective, were often hard for humans to read. And it tended to mix languages, like jumping between English and Chinese in its thought process.
So powerful, but maybe a bit alien and messy. Kind of. Functionally brilliant, but not always clear or consistent for human use.
So how do you take that raw, emergent reasoning power and make it more, well, usable, accessible, understandable for humans?
That's exactly what the main DeepSeek R1 model aimed to do, building on R10's lessons. It addresses those issues by adding a tiny bit of cold start data.
Cold start data.
Yeah, not huge data sets, just a few thousand carefully chosen examples of high-quality, long chain-of-thought reasoning. It acts like a gentle nudge, giving the model a hint of human-style reasoning before the big RL phase starts.
Just a little bit of human guidance at the beginning.
Exactly. Then they apply the same efficient GRPO reinforcement learning, but with a crucial addition, a language consistency reward.
Ah, to fix the language mixing.
Right. It actively encourages the model to stick to the target language during its reasoning, making the output clear and coherent for humans. It's about balancing that raw power with alignment to human preferences.
Making its thoughts effective and understandable. Did they refine it further?
Yes, they added a second, more general RL stage. This focuses on broader human preferences, helpfulness, harmlessness, general usefulness, while still honing its reasoning across all sorts of prompts.
So specialized rewards for math and code, but also broader rewards for general conversation.
You got it. Rule-based rewards for the precise stuff, advanced reward models for the more subjective, open-ended interactions. It makes R1 not just a strong reasoner, but a versatile, helpful, and safe AI overall.
Okay, so this refined DeepSeek R1, how does it stack up against the other big players? For you listening, where does it sit in the current LLM landscape?
It's right up there at the cutting edge. On reasoning tasks, its performance is comparable to OpenAI o1-1217, which is a major benchmark.
Comparable to OpenAI's specialized reasoning models.
Yes, but it's broad, too. It beats their earlier DeepSeek V3 on STEM questions, showing deep science and math understanding. It excels at long context QA, like on the Frames benchmark, suggesting strong document analysis skills.
What about other areas like writing or general chat?
It does really well there, too. Significantly outperforms DeepSeek V3 on benchmarks like AlpaKival 2.0 and ArenaHard, which test open-ended conversation and writing. This shows the generalization benefits from that large-scale RL. It can apply its smarts across a much wider range of tasks.
That's impressive breadth. And its core strengths in math and coding algorithms, did R1 maintain that edge from DeepSeek Coder?
Absolutely. On math tasks like AIM 2024 and Math 500, it performs on par with OpenAI o1-1217, significantly ahead of many others.
Dominant in math.
And the same story for coding algorithms, Live Code Bench, Codeforces. It dominates those benchmarks, again comparable to OpenAI o1-1217.
So top tier in reasoning, math, and algorithms.
Definitely. Now, they acknowledge there's still work to do on the more complex engineering-focused coding tasks, the ones involving huge code bases. But its current performance clearly signals its advanced reasoning power in quantitative and logical domains. It's a real testament to what RL can achieve.
Okay, so from general reasoning, let's zoom back in a bit to that crucial domain, mathematics. You mentioned DeepSeek Math earlier. Tell us more about that specialized model.
Right, DeepSeek Math was their dedicated effort to really push the boundaries, specifically for mathematical reasoning. They were incredibly careful validating the math data they used for training.
And you mentioned an interesting finding about ArcSIF papers.
Yeah, that was quite counterintuitive. They found that training on a huge pile of ArcSIF papers, which seems logical for math, right, actually didn't give them noticeable improvements on their math benchmarks.
Really? Why do you think that is?
It suggests maybe just a raw volume of academic papers isn't the key. Perhaps the style of ArcSIF papers, very formal, polished, lacks the sort of messy, step-by-step problem-solving context you find in other math resources. It implies the type and quality of data matters more than just quantity from certain sources.
A lesson there about just throwing data at the problem. So how did DeepSeek Math actually perform?
The DeepSeek Math-based 7B model, despite being only 7 billion parameters, achieves state-of-the-art results across many English and Chinese math benchmarks.
State-of-the-art at 7B.
Yeah, significantly outperforming previous leaders like Mistral and Lemma in that space. And this is really critical for you, the listener. If your work involves data analysis, scientific computing, finance, anything needing reliable math problem solving from AI.
Having a dedicated math specialist AI could be a game changer for precision and efficiency.
Absolutely. Imagine it handling complex calculations, verifying steps, even spotting logical flaws in quantitative workflows. It frees you up for higher-level thinking.
Okay, so these big models like R1 are incredibly powerful reasoners. But running a massive model isn't always practical for everyone. How do we get that intelligence into more accessible forms?
That's where distillation comes in, and it's a really clever, practical approach.
Distillation, like distilling spirits.
Sort of. You take the complex reasoning abilities learned by a big, powerful teacher model, like DeepSeek R1, and you effectively transfer or distill that knowledge into smaller, much more efficient student models.
Teaching the small models the tricks learned by the big ones.
Exactly. DeepSeek AI did this for a range of smaller models, from 1.5 billion up to 70 billion parameters, using base models like Qwen 2.5 and Llama 3. It's like an experienced mentor passing wisdom to a nimble protege.
Making the knowledge more widespread and efficient. How well did these distilled student models perform? Did they lose a lot in the process?
That's the striking part. They performed incredibly well, often punching way above their weight class.
Really? Give me an example.
Okay, DeepSeek R1 distilled Qwen 7B. That's a 7 billion parameter model distilled from R1. It actually outperformed larger open source models like QWQ32B Preview, which is over 4 times its size, on reasoning tasks.
Better than a model 4 times bigger.
And even more impressively, on tough math benchmarks like AIM 2024 and Math 500, this 7B distilled model surpassed super capable non-reasoning models like GPT 4.0.0513 and Claude 3.5 Sonnet.
Wow, that shows the reasoning capability really transfers effectively.
It really does. It's a testament to how you can compress that high-level reasoning from a giant teacher into a smaller student.
So does this mean distillation is just better than trying to train a smaller model directly with reinforcement learning? Is it always the way to go?
That's key insight from their research. They compared training a smaller model, say Qwen 32B, directly with massive RL versus just distilling into it from Deepseek R1.
Yeah.
They found direct RL on smaller models, while powerful, needs enormous computational power.
Yeah.
And even then, it might still not match the performance of the model simply distills from the better teacher.
So distillation can be more effective and much cheaper computationally.
It strongly suggests that, yeah. So for you, the listener, this means distillation is a highly economical and effective way to deploy advanced reasoning. It puts sophisticated AI within reach on less powerful hardware, enables faster results, and lets you integrate this intelligence into more apps without needing a supercomputer or huge cloud bills. It's about democratizing the smarts.
Getting top-tier intelligence into more places makes sense. But, AI development isn't always smooth sailing. It's easy to focus on the wins, but sometimes understanding what didn't work is just as valuable, right?
Absolutely. Learning from the challenges is crucial.
What unsuccessful attempts or roadblocks did the DeepSeek AI researchers share? It's always insightful when teams are open about that.
They were commendably open, actually. One area they explored deeply was process reward models, or PRMs.
PRMs rewarding the steps, not just the final answer.
That's the idea. Guide the AI's reasoning step by step. Conceptually nice, right? Encourage human-like thinking. But they hit major practical hurdles.
Like,
Well, for general reasoning, defining clear universal steps was really hard. And even if you could, figuring out if an intermediate step was truly correct was incredibly difficult. Automated checks were noisy, manual checks were just impossible to scale.
hard to give reliable feedback mid-process.
Exactly. And it led to reward hacking. The model finds clever ways to get the intermediate reward without actually solving the problem properly.
Like gaming the system.
Kind of. Plus, adding a whole separate PRM model just makes the training pipeline more complex and computationally expensive. It highlighted how tricky it is to align AI with fine-grained, human-style reasoning across the board.
Okay, so PRMs were tough. What else did they try that didn't quite pan out as hoped? Any other big ideas?
They also explored Monte Carlo tree search, MCTS, inspired by AlphaGo's success in Go and chess.
Ah, the game-playing search algorithm. How would that apply to language?
The idea was to have the model break down answers into parts and explore different continuations searching for the best path. But the problem is, for language generation, the search space is exponentially larger than in a game like Go.
Way more possible moves at each step.
Exactly. At every single token, thousands of possibilities. The models could easily get lost down rabbit holes or stuck in local optima, finding a decent path but missing the truly best one because the space is just too vast to explore fully.
And guiding that search is hard too.
Very. Training a good value model to estimate the quality of partial answers, which is key for MCTS, proved really difficult for the fuzzy nature of language, unlike the clearer board evaluations in games.
So these attempts show the frontier challenges. It's not just about scale, it's about navigating these complex learning dynamics. Valuable lessons learned, even from the things that didn't work perfectly.
Absolutely. Understanding these roadblocks gives you a much deeper appreciation for the difficulties involved in building truly intelligent systems.
So given all this, the powerful models, the lessons learned, what's the picture for the immediate future? What limitations are they still working on, and where are the next breakthroughs needed?
They're quite upfront about limitations. One practical point for you using DeepSeek R1 is prompt sensitivity.
It's picky about prompts.
It can be. And interestingly, they found few-shot prompting, giving it examples, actually hurts its performance sometimes.
That's backward. Why?
Their hypothesis is its internal reasoning is so strong that explicit examples might actually constrain it unnecessarily. So their advice for you is use zero shot. Just describe the problem clearly. No examples needed.
Good to know. Zero shot for R1. What about coding? You mentioned it's great at algorithms, but maybe less so on broader engineering tasks.
Right. While it nails algorithmic problems like on code forces, it hasn't shown the same dramatic gains on tasks involving large, complex code bases,
Huh?
like refactoring or debugging in big systems, tested via tools like Aider or SW Verified.
Why the difference?
They think it's mainly because evaluating those complex engineering tasks takes a long time.
Yeah.
That slows down the feedback loop in reinforcement learning, making it harder to learn effectively. But it's a clear area they're working on,
Oh.
exploring things like rejection sampling or asynchronous evaluations to speed up the feedback for those complex coding scenarios. Making it better at real-world software engineering is definitely on the roadmap.
And what's their big picture vision? The unifying idea behind the coders, the reasoners, the math specialists?
Their core belief, which they state clearly, is that the most effective code-focused large language models are those built upon robust general LLMs.
Meaning strong general intelligence is the foundation for specialized skills like coding.
Exactly. To really understand and execute complex coding tasks, the AI first needs a deep grasp of human language, intent, common sense. Coding isn't just syntax, it's translating human needs into logic.
So general AI and specialized AI need to grow together.
That's the vision. Increasingly powerful general LLMs as the base, enabling even better, openly shared specialized models on top. A holistic approach.
Wow, we've covered a huge amount today. From Deepseek Coder writing impressive code and solving math problems to Deepseek R1 having that incredible aha moment of emergent reasoning,
Uh-huh.
and then the cleverness of distillation,
Yeah.
packing that intelligence into smaller models that you can actually use more easily. It really feels like we're seeing advanced AI become not just more powerful, but genuinely more accessible.
And if we just step back and connect this to the bigger picture, think about it. LLMs can now write complex code, solve advanced math, show emergent reasoning, self-correct, learn complex strategies on their own.
Yeah.
So what previously unsolvable problems do you think suddenly become tractable? What new kinds of human-AI collaboration might we see emerge in just the next few years as these capabilities get even better and more widespread? The possibilities seem, well, pretty immense.
A provocative thought to leave us with. The frontier is wide open. That's all the time we have for this deep dive. Thank you so much for joining us on this exploration of the DeepSeek models.
My pleasure.
We hope this gave you a clearer view of the cutting edge of AI and maybe inspires you to continue your own deep dive into these fascinating topics.